So this is two-dimensional motion. And it's motion where the only force acting is gravity or weight. So if you think back to that GIF or GIF animation, whatever you want to call it, the only force acting when the person was in the air was his weight going down, or her weight, I think you can tell, was their weight going down. Obviously, when they're on the trampoline, there's another force, but when they're in the air, the only force is gravity, right? So what this means is we usually ignore air resistance. So here's a ball being thrown. All right, it will go through the air, it will land. All right, when it's in the air, we say it's undergoing projectile motion. So when I'm here holding it and throwing it, all right, there is a force on it. And then when it's in the air, the only force on it is its weight, right? There's no other force on it in the air. And I'm repeating myself, and you might think this is really obvious, but it's really worth stressing. Right? A lot of people will say, well, here there must be a force making it go forwards. Well, there's no force on it other than gravity making it come down. There's a force here that makes it move to start with, but there's no force here other than work rate. All right. Now, obviously, if we looked at air resistance, so this is no air resistance. If we looked at air resistance, then it would do something like this. Right, it would make it go lower and it would make it go shorter. You might know what shape it goes in the air. Usually in school, I would often show you a quick demo, which kind of, and we can nicely prove that it is actually this shape. But for now, you'll just have to believe mathematically why. All right, it's a parabola. All right, so it follows something like this: y equals x squared. Right, that's a parabola. So how do we analyze this? So this is not hard as long as you basically follow a set method. So the kind of way to solve it, and this is the most important step, is you treat the horizontal and vertical motion independently. So that means you solve something horizontally, great, you got an answer, brilliant, right? And then you kind of stop thinking horizontally, you start thinking vertically, and then you solve that bit, right? And you don't mix them up. So horizontally, what do we know? Well, let's redo our sketch. So horizontally, it's going this way. So it's going to have a speed of v cos theta. All right, we want the horizontal component of the speed. There's no air resistance. So what does that mean? That means that it travels at a constant speed. So we can use velocity is displacement over time to work out how far it goes, or its time, or its distance, or its speed, or something. And that's basically all there is to it horizontally. Vertically, what is happening? Well, it's traveling upwards with a velocity of v sine theta. Again, there's no air resistance. And if it's just going vertically, it will go up, it will reach the top, it will come back down again. Right, so what can we use? We can use SUVAT from last lesson to analyze the motion. So for example, time of flight, which equals the time in the air. Now, I've said time of flight because that's a phrase that is used a lot. Or its height, or other things. Very often, the step one is we're doing this to find the time. That's really, really common. And then we use the time here to find the range or the distance. That's a really, really common way of solving something. You use this to find the time, use the time in this one to find the range. Because obviously when it hits the ground again, its time is over, so it's going to stop. Are there any questions at this stage? All right, let's look at a couple more things. So if you want the maximum range of something, then the angle should be 45 degrees. That's just kind of a fact that I kind of assume people know, but sometimes people forget. All right, the max range is 45 degrees. It's a nice trade-off between time and distance. If you go any higher, it will do this, and if you go any lower, it will do this. If you want the max range, but you're trying to throw it onto something higher, all right, then the angle becomes greater than 45 degrees. It obviously depends on how high this is and how far away you are. But what you need to do is if you go any lower, or at 45, it will hit this. And again, if you go any higher, it will do this, but this angle is more 45. And then if you're going the other way and you're throwing off a cliff, again, the max range corresponds to an angle less than 45 degrees. Right, if we throw it at 45 degrees, we're kind of wasting some of our throw because we could get it further because it's got this extra height to fall. And if we throw it too low, it will just go straight down here. So the angle becomes less than 45 degrees. Now, I just want you to have a quick look at this slide on the board. This is a table of values of G around the world. I think this is just quite nice to show you because we obviously use G as 9.8. But if we look at Great Britain down here, right, you can see it's 9.8144. But you can see it actually varies quite a lot in the world. So if we pick somewhere like Bolivia, it's actually 9.78. Now it rounds to 9.8, right? But it's less. It's actually like 3% less. If we look at somewhere like Denmark, Copenhagen is actually 9.82. So it's, 1% higher. Which for in everyday life, no one notices, no one cares. We round it to 9.8, great. But this does make a difference. If you're doing a really sensitive scientific experiment, like what the sort of things they do in CERN, or there's a laboratory in Teddington where they do really sensitive experiments, this matters, and you actually do need to adjust your value of gravity in calculations. So in this laboratory in Teddington, the National Physical Laboratory, they have equipment so sensitive that some of their experiments they have to do at night, because during the daytime, when cars and lorries are going past the road, the vibrations affect their experiments. At CERN, when they are looking at the collisions of protons and so on, their equipment is so sensitive that they have to adjust for the gravity of the moon as it goes around the Earth, and they have to adjust for the gravity of the tides in the lake that's near to them. So if there's more water or less water, it will affect their experiments. And actually, you could probably see that, or think of a way this might affect humans as well. If you're like an Olympic high jumper, you're much more likely to break a world record in Bolivia, for example, because you've got a 3 or 4% advantage over someone competing in Denmark, right? And for someone at an Olympic level, 3 or 4% is actually quite a lot. But as I said, everything rounds to 9.8, which is why we use 9.8 in calculations. All right, last two things. Just a quick activity for you. I just want you to sketch a couple of graphs, just to check you've been paying attention. So firstly, horizontally for a projectile, what is its displacement time graph going to look like? And what is its velocity time graph going to look like? And then secondly, vertically, what is its displacement time graph going to look like? And what is its velocity time graph equal to? All right, horizontally, as we said, it's a constant, sorry, that's wrong. It's a constant speed, so the displacement increases at a constant rate, and the velocity is constant, so it's going to be a horizontal line. Vertically, our displacement is going to increase, and then it's going to decrease and go back to 0. All right, because vertically, remember, we're just looking at it going up and down, we're ignoring its horizontal motion. And then its velocity is the gradient of this graph. So it's steep, and then it's decreasing, decreasing, it'll get to 0, and then it will increase and increase, but negatively. So it should look something like this. I could, I suppose, also have done acceleration time. Horizontally, there's no acceleration, so it'd look like this. And vertically, what is the acceleration? It would be like this. It would be minus 9.8, right? Because we're accelerating down all the time. Maybe I should have put those on. All right, are there any questions on anything I've just said? Okay, please, can you go into the lesson? And could you please complete task 1 and task 2, which are some worked examples. So try the questions, watch the answers to the video. Then there is a short worksheet that has a couple of more worked examples on and some very quick questions. And then for task 4, you have an option. You can either do the further practice that's on 15 and 16 of the PowerPoint, or if you've been finding it all really straightforward, I have some more challenging questions that I will give to you just to let me know when you get onto it. I would expect this would take probably about an hour to complete. If you have any questions, obviously ask them. Otherwise, I will kind of let you get on with it for about an hour before I talk to you again.